All right, let's dive into something that's so basic you probably haven't even thought about it since, I don't know, high school physics class. I'm talking about inertia. We all kind of get it, right? Things just keep doing what they're doing unless something messes with them. But have you ever stopped to ask why? It turns out that simple little question is one of the biggest, deepest mysteries in all of science. And we might just be getting a new answer that could change how we see reality itself.
So, before we can really start pulling this idea apart, we need to get on the same page. Let's start with the absolute foundation, the rule that's basically governed how we think about motion for hundreds of years.
Yep, you know this one. It's Newton's first law of motion. It's clean, it's simple, and it just works. It works for a soccer ball rolling across a field, and it works for a planet hurtling through space. It's perfect.
And for over 3 centuries, this has been the bedrock. It's what scientists call a postulate, which is really just a fancy way of saying this is a rule we all agree to accept because, well, it works. We don't explain it, we just use it. But here's the twist. You see, just because you accept a rule doesn't mean you actually understand it. And it turns out, inertia is one of the oldest, most stubborn cold cases in the history of physics.
Why? Why does nature behave this way? What's so special about staying still or moving in a straight line? Why does an object fight you when you try to speed it up or slow it down? Newton himself had no idea. He famously said he wouldn't even guess at the cause. And for hundreds of years, nobody else had a good answer either.
And here's what's so wild. Even our most brilliant, powerful theories couldn't quite crack it. Classical mechanics, it just states inertia as a given. Einstein's special and general relativity, they describe the effects of inertia with this beautiful geometry of spacetime, but they never really explain where that geometry comes from. And quantum mechanics, it basically just inherits the whole problem without offering a solution.
So if our greatest theories can't give us the answer, where do we even look? Well, a newer idea, called dynamic vacuum field theory, or DVFT for short, suggests the answer isn't in the object itself or even in spacetime. It's in the very fabric of reality, the vacuum.
Okay, let's walk through this, because the logic here is actually pretty cool. First, stop thinking of a particle as a little marble. Instead, picture it as a stable, humming pattern in the vacuum field. Got it? Okay. Second, when that pattern is just gliding along at a constant speed, the whole shape moves together perfectly, no problem. But, and this is the key, when you try to accelerate it, you're trying to bend or deform that pattern. And number 4 is the punchline. The vacuum itself pushes back. It resists being deformed.
So what this all means is that for the first time, inertia gets a physical cause. It's not some mysterious property baked into matter. It's the stiffness of the vacuum. It's the energy you have to pay to literally warp a tiny piece of reality's fabric.
Now that is a massive claim, I know. So how does this whole idea of vacuum stiffness really stack up against the titans of physics, like Einstein and the Higgs field?
This really gets to a core difference in what they're trying to do. Einstein described how inertia works. He said objects follow the straightest possible path through curved spacetime. It's a geometric description. DVFT is trying to answer the next question. Why does spacetime have those properties to begin with? It's trying to find the physical engine running underneath Einstein's geometry.
And it's a similar story with the Higgs field. The Higgs is amazing. It explains why certain particles have mass when they're sitting still, but it doesn't really explain inertia itself. I mean, think about it. A photon has no mass, but it definitely has inertia. Its motion persists. DVFT offers an explanation that could work for everything, whether it has mass or not, because it's not about the particle itself. It's about the vacuum it's traveling through.
Okay, so this is where we take a step back, because this new way of thinking turns inertia from just a simple rule of motion into something way, way more profound. It becomes a statement about what it means to exist.
I mean, really think about that for a second. When an object has inertia, what it's fundamentally doing is saying, I am going to continue to be what I am, unless something powerful forces me to change. It's a principle of continuity. It's an object's identity persisting from one moment to the next.
Can you even imagine a universe without inertia? It would be pure chaos. Things would just randomly speed up, slow down, or change direction for no reason at all. The very idea of an object would be unstable. Cause and effect would completely fall apart. So you see, inertia isn't just a law of motion. It's the physical bedrock of order in our universe.
Here's probably the most powerful way to put it. The vacuum has a tendency to preserve the patterns within it. It remembers its own state from one instant to the next. And that resistance to forgetting, that deep, fundamental tendency to endure, that's what you and I experience as inertia. So,
Where does this leave us with that old law we learned back in school? It means we're making a huge leap from just accepting a rule to finally understanding the reason for the rule.
In the end, this completely transforms Newton's first law. It stops being a postulate, an assumption we have to make on faith, and it becomes a theorem. It becomes an unavoidable consequence. If you start with the idea of a symmetric, uniform vacuum, then it follows that uniform motion doesn't cost any energy, and the law of inertia just naturally pops out. It has to exist.
And that right there is the deepest takeaway. This whole journey isn't just about figuring out why a hockey puck slides on ice. To explain inertia is to explain why the universe has continuity, why it has structure, why this moment is connected to the next. It's about explaining why reality itself holds together.
Which leaves us with one final, pretty mind-bending question to chew on. If the fabric of space itself has a property that acts like memory, a tendency to preserve structure and information, what other secrets might be written into it? What else is the vacuum remembering?